We've already talked about how melting point and boiling point are affected and usually measured, or basically a way that we can measure how strong intermolecular forces are between two molecules. Now we're going to talk about the other ways. So this first way is viscosity. Viscosity, as many of you have told me, you think of it as like the thickness, which is not wrong. The technical definition is the resistance of a liquid to flow. So generally, if we think of something like honey or syrup, it's very slow to move. So we think of it as very thick. It just doesn't flow very easily. So when things are able to move past each other easily, then their forces, or IMFs, are not as strong. But if molecules have really high intermolecular forces, then it's going to be harder to move past each other. So viscosity increases with higher or stronger intermolecular forces. And if we increase the temperature, then we're getting those molecules that are able to move around easier, so the viscosity will decrease. So viscosity goes down with an increase or a higher temperature. So here we see hexane, all these hydrocarbons. What's changing in them is how big they are, right? So their molar mass and the length of their chain, so bigger surface area. So we would increase that as we go down. We're increasing LDFs. And we can see that our viscosity also increases. So we have 3 times 10 to the negative 4 all the way down to 14 times 10 to the negative 4 for decane. Next property that we're going to talk about is surface tension. So it is the force that is felt on the surface. So water has a really high surface tension, so basically it's almost as if there's like a skin layer, and that's due to extra inward forces on the surface. So when we have a molecule inside, there are forces acting on every surrounding molecule. When we have a surface molecule, the forces are felt on the surrounding molecules, but there's nothing to counteract on the surface. And so because of that, there's extra force being pulled downward, and so that molecule feels that downward pull. This is what causes water to bead up when it contacts a nonpolar surface. So here we see down here, the molecules feel the inward pull, and so in order to kind of minimize those repulsions and maximize attractions, it forms a bead or a sphere. The downward force that it feels, that leads to that surface tension. So molecules that have stronger intermolecular forces are going to have a stronger downward pull on the surface molecules, and so they'll have higher surface tension. The next thing we're going to talk about is cohesion and adhesion. When we think of the root word adhesion, we think of like something sticky. The term co means together, and the prefix ad means toward. So cohesion means sticking together, molecules' attraction to itself, and adhesion means molecules' stickiness toward another thing. So in this case, it'll be surfaces. So molecules are going to bind to other molecules with cohesive forces. And when the molecules bind to the surface, that's where we get the adhesive. These are particularly important inside capillaries. So capillaries are narrow tubes, and because they're narrow, the adhesive and cohesive forces are both going to matter. Because in a narrow tube, we have a surface on both sides in all directions, and because it's narrow, the distance between the sides of the tubes is going to matter. So adhesive forces are going to be what cause the molecules to attract to the surface of the wall and therefore climb the wall if there's attraction there. Cohesive forces attract the liquid to itself, so keeping it together. I really like this image here. So water has strong, so if we look at this picture here, we'll zoom in. So you can see that the water is climbing up the wall due to this concave meniscus. So it looks like so we have it's literally sticking to the surface, and it's sticking stronger than it is to itself, causing that concave meniscus. Now mercury has a convex meniscus, which means that it doesn't have as strong of adhesive forces to the surface of the test tube, and it rather has stronger forces to itself, so stronger cohesive forces. And it's really due to the interactions with those liquids to the glass. So glass has some oxygens on the surface, so oxygen hydroxyl groups really, and so water is the polar water molecule is going to interact with that. For mercury, it doesn't have any attraction to the wall, but it does have attraction to itself, so it's not going to have any adhesive forces, and therefore it'll just have cohesive and stick to itself, causing a convex meniscus. So we can tell by the shape that it takes that water has stronger adhesive forces with glass, and mercury has stronger cohesive forces with itself. When we go from one phase to another, that's called a phase change. So to do a phase change, you either have to add energy or energy will be released. When we add energy, that's an endothermic process. And releasing energy is exothermic. We can see all of these blue lines where we're going from low energy to high energy. Those are those endothermic processes, and the reverse is exothermic. So the phase changes we have are melting and freezing, that's going between liquid and solid, condensing and vaporizing, going between liquid and gas, and then subliming and depositing, which is going from solid to gas or gas to solid. Keep in mind also, another more scientific term for melting is fusion. Doesn't really make a lot of sense, but I guess kind of, the more you get used to it. Anyway, so those will be interchanged, but the opposite of that would be freezing. We have these different thermodynamic values that tell us the amount of energy that it takes to change phase, and that's the heat of fusion, the heat of vaporization, and the heat of sublimation. So the heat of fusion is the energy it takes to change a solid at the melting point for that substance to a liquid. The heat of vaporization is the energy it takes to change a liquid to a gas at its boiling point. And the heat of sublimation is the energy to go straight from a solid to a gas. You can see that these values are related to the intermolecular forces. So the stronger the intermolecular forces, the higher the energy it takes to do that. And then you can also notice that it takes a lot less energy to melt something than it does to vaporize. We'll talk about why soon. And then if you want to find out the heat of sublimation, you can just add together the fusion and vaporization values. So why do you think it takes more energy to go from a liquid to a gas than a solid to a liquid? So if we think about it on the molecular standpoint, when we go from a solid to a liquid, we are still staying those molecules are still staying together. We're just getting them from being completely rigid to being able to move around. So when you're just able to get them to flow, you're not really completely breaking intermolecular forces, so that doesn't take as much energy. Now, if I want to take my liquid and get it into a gas, I have to get these molecules to move around enough for them to break off from their liquid phase. And that takes a lot more energy to completely break apart versus like slightly break away, so you're still together. So we can see here is what we call a heating curve, and this is a graph of temperature versus the heat that we add. You'll notice you'll see different things going on here. So first of all, when we have a change in temperature, when the temperature rises, and so these blue lines, that's when we're specifically heating our substance. And you're familiar with that because we've done that in thermo. We know that the heat that we add to change our substance is related to the specific heat times the mass times that change in temperature. So when we see these slopes, these areas of slopes, that's when we're just heating. We're staying in the same phase and we're heating. So you'll notice we have, for water here, we have solid ice that's heating. Then we have liquid, water, and then after that we have steam. So those are the different phases. When we're undergoing a phase change, the temperature of the substance does not rise during that phase change. It stays constant. So these red areas, let's see them here and here, these flat lines, that's when we're having a phase change. So when we go from B to C, we're melting. If we went from C to B, we'd be freezing. D to E is evaporating, and E to D would be condensing. When we want to find the heat for that, we need to use the enthalpy values that we talked about on the last slide. So the heat, when we do phase change, is equal to the amount of moles that I have times the delta H, either vaporization if we're up here from D to E, or fusion if we're in the B to C area. So you can see those here. So when we have temperature that's changing, we'll use the temperature change one. When we have temperature that's constant, we'll use the enthalpy of vaporization or fusion. And if I go from like point A to point F, I'm going to heat my solid ice. I'm going to then melt it, and then I'm going to do another equation. So for every little segment on the line, we have to do an equation, and then we'll add them all up. So let's practice it. I want to know the enthalpy change upon converting 1 mole of ice at negative 25 Celsius to 125 Celsius under a constant pressure of 1 atmosphere. Okay, so this is important. The specific heat of ice, so C of ice, is 2.03 joules per gram degrees Celsius. C of water, liquid water, you're familiar, 4.18 joules per gram degrees Celsius. And C of steam is 1.84 joules per gram degrees Celsius. Then we have delta H fusion. So the melting is 6.01 kilojoules per mole. And delta H vap is 40.67 kilojoules per mole. So I need to calculate the enthalpy. So I'm going to draw a little curve. So I'm going from negative 25 up to 125. So I want to also think about where those phase changes are happening. Now we're very familiar with water, and so we know that we're going to have a phase change at 0 and 100. So I'm initially going to heat it, phase change, heat it, phase change, heat it. So I'm going to have, because I have 5 little segments. I'm gonna have 5 equations. So I'm gonna label them 1, 2, 3, 4, 5, so we can see what's going on there. So for 1, since I'm heating and I'm changing the temperature, I'm gonna use Q equals Cm delta T. So I'm gonna have the specific heat of ice, 'cause that's where we're at down here, is 2.03 joules per gram degrees Celsius. I need my mass. So I have a 1 mole of ice, so I need to find out how much that weighs. So I'm gonna use 1 gram, 1 mole. I'm gonna use a molar mass of water for every 1 mole. It's 18.02 grams. So I'll plug that in, 18.02 grams. And then my change in temperature, I'm going from, to 100, so I gotta do final minus initial. So I'm gonna end at 0 degrees Celsius minus -25 is where I started. So I'll have 2.03 times 18.02 times 25, and I get that I need to add 914 joules. So I will highlight that. Okay, now for segment 2, I'm gonna have my heat. I'm doing a phase change, so it's gonna be N times delta H, and I'm melting, so fusion. So I have 1 mole. Delta H fusion is 6.01 kilojoules per mole. So that gives me 6.01 kilojoules. So there's another one. For segment 3, I have another temperature change. So Q equals Cm delta T. So now my C is 4.18 because I'm at water now. My mass is still 18.02, and then I'm going to 100 degrees Celsius from 0, so it's 100. So I calculate that, and I get 7,520 joules. I'm gonna get rid of this calculation so I have some room. Okay, so now I'm gonna have another phase change after I get to 100. So for number 4, I'm evaporating. So I'm gonna use Q equals N delta H vap. So now I still have 1 mole times by 40.67 kilojoules per mole. So I have 40.67 kilojoules. Highlight these numbers. And then the last one, now I'm heating it up a little bit more. Q equals Cm delta T. I'm changing the temperature. And now my specific heat for steam is 1.84 joules per gram degrees Celsius. I have 18.02 grams. And I'm going up to 125 from 100. So a change of 25. And that gives me an amount of energy that's 830 joules. So if I want to find out how much energy it takes to do total, I need to add them all together. Now notice I'm in joules for some and kilojoules for others. So what we'll want to do is convert each of these joules to kilojoules by dividing by 1,000. So I get 0.914 kilojoules. 7.52 kilojoules, and 0.830 kilojoules. So now my total heat is gonna be 0.914 plus 6.01 plus 7.52 plus 40.67 plus 0.830. All of those are kilojoules. which gives me a value of 56.0 kilojoules. So you can see the biggest amount of energy came from evaporating it. That's pretty wild, which makes sense because we got to break those IMFs. Okay, so now we're going to find out the process to go from 100 grams of water at 50 cooled to ice at 30, negative 30. So here we're having a cooling curve. So I'm going from 50. I'm gonna go down to 30, so I'm gonna cool it. I'm gonna melt it or freeze it, and then I'm gonna cool it even more. So 50, I gotta go down to 0, and then I gotta go down to negative 30. I like to draw it so that it helps me visualize my breaks and stuff that I'm gonna have to do, because we're not always gonna be using water, and it's not always gonna be this nice and pretty. So here I have, I'm gonna have 1, 2, 3 segments. So again, we have delta H. We're only going to need to deal with freezing. So we're gonna do delta H of freezing. It's gonna be negative delta H of fusion. So that's a negative 6.01 kilojoules. Which makes sense, because if it takes that much energy to melt something, then it should release that much energy when we freeze it. And then I also have C of water is 4.18 joules per gram degree Celsius, and C of ice is being 2.01 joules per gram degree Celsius. Okay, I need that information. So now for step 1, I'm cooling, so I have CQ equals CM delta T. We're still going to use it. Everything should work out nicely with the change in temperature. So C is 4.18. And then we're going to have the mass is 100 grams. And then we're going from 50 to 0. So 0 minus 50. So that gives me negative 2,900 joules, which we know we're going to kilojoules, so I'll divide by 1,000, so 20.9 kilojoules here. Now for segment 2, I have to freeze, so I'm going to have Q equals N times delta H freeze. So I need to find out how many moles. I have 100 grams. I'm going to go from 18 grams, 18.02 grams per mole. So 100 divided by 18.02, and that gives me 5.55 moles. So 5.55 moles times by negative 6.01 kilojoules per mole, which is negative 33.35 kilojoules. And then the last segment, we're going to be cooling even more. So Q equals Cm delta T. We're going down to negative 30. So I have my C of ice is 2.01 joules per gram degree Celsius times by 100 grams. And I'm going from 0 to negative 30, so negative 30 minus 0. So that should give me a negative number. 2.01 times 100 times negative 30 equals negative 6d30 kilojoules, which we can do is negative 6.03 kilojoules. So add all those together, our total amount of energy will be negative 20.9 kilojoules plus negative 33.35 kilojoules plus negative 6.03 kilojoules. And And that gives me a total of negative 60.3 kilojoules. Okay, so that's how we do these. So now you've seen when we go heating it and when we cool it, the only difference is we'll just change the enthalpy of freezing and for freezing and condensing to be the opposite of fusion and evaporation, but the steps will still work.